This program is brought to you by Stanford University.
The Asteroid Challenge was through astrobiology, as Lynn just mentioned. The connection is obviously that I realized that, oh yeah, well, that's right. Just keeping with the times of current cartoon. And I'll be speaking from under two hats today. You'll come to appreciate that as we go on. But there's basically the Association of Space Explorers, which is our professional organization of astronauts and cosmonauts from around the world, and B612 Foundation. Some of you may be aware that B612 was the asteroid that the Little Prince and his Rose came to Earth from. And so when we got together, we named our foundation after the Little Prince, or the Little Prince's home. The breakdown here is pretty straightforward. I mean, the Association of Space Explorers is a bunch of astronauts and cosmonauts, local heroes from 34 countries, and that may be a big deal to other people. To us, it's more than anything else a way that you can open a door, almost any door you want, once. You better have something worth saying, or it doesn't open again, but at least you can get attention to things that you care about if you play that right. So given that the whole issue of dealing with, in a very operational sense, dealing with deflecting asteroids away from impacts from Earth is a geopolitical challenge. It's not just a technical challenge. In fact, the technical challenge is simple compared with the geopolitical issues. And recognizing that, I felt that the Association of Space Explorers was in a pretty unique position to be able to take on the international political issues. B612 Foundation, on the other hand, is looking at and has contributed to the whole issue of physically deflecting asteroids. How do you deflect asteroids? Can you deflect them? How do you do it? What do you do? What do you have to do? When do you have to do it? Et cetera, et cetera. But this is the physical aspect of the challenge of keeping asteroids from hitting the Earth. Okay. Yeah, we don't take questions of clarification from outside. Okay, so just very quickly running through, I mean, this is all pretty obvious stuff, land, oceans, and atmosphere, and all of them have natural hazards, and we're gradually becoming accustomed to pictures like this. One thing I like to ask people to do when they look at these pictures, I mean, these are real pictures. And while that one is pretty abstract, as is the one above it to a certain extent, although somebody had to take that picture, this picture and this picture, put yourself in the place of those people. They're real people. And I mean, these are pretty frightening natural disasters, and they wipe out a lot of people. They're a lot more frequent than the kind of thing that we're talking about with asteroids, but at the same time, even an incredible thing like the Indian Ocean tsunami and Hurricane Katrina or whatever, these things, even at their largest scale, are small in comparison with the magnitude of the disaster when the Earth gets hit by an asteroid. So yeah, they're less frequent, but they're a heck of a lot more damaging. So, in fact, I gave a lecture at the California Academy of Sciences, where Lynn is very familiar with. It wasn't a lecture, really. I was on the board of trustees of the Academy, and I argued very strongly back 4 or 5 years ago that natural history, I mean, here we are, Darwin's birthday, wonderful, but natural history is a lot bigger than we have thought up until this time. Natural history has always been restricted to things like what we just saw. The natural environment, land, oceans, atmosphere, etc. the fact of the matter is that we're embedded in a cosmic environment as well, and we're coming to understand that, in fact, there are cosmic phenomena which affect the Earth, affect life on the Earth, and in fact, in some cases, are hazards. Certainly, solar flares can wipe out your cell phone, or your, used to be pagers. People don't have pagers much anymore. You know, comets once in a while hit, and near-Earth objects, of course, hit with much greater frequency, about almost 100 times the frequency with which comets hit. So there are space natural hazards that we're gradually coming to understand. And this particular one is the one which, in my early interest in astrobiology, got me into this, because you don't study astrobiology very far before you recognize the tremendous impact, right? The tremendous effect that impacts of asteroids and comets had on both the enabling of life on the planet and, since it's enabled, destruction of it as well as enabling. The particular, Lynn, I don't know whether you're aware of this, but the particular thing that really got me into this was one of the Dean lectures one night at the Morrison Planetarium at the Academy back, 10 years ago, I guess, by Norm Sleep, I mean, from right here at Stanford, or at least he was. Is he still here? Norm's still here? Yeah. Have you, I don't know whether you had Norm as a lecturer, but Norm gave a lecture there. I just went, interested in astrobiology. He's talking about impacts. Obviously, impacts are important. Well, Norm was the first one who really got into my head the tremendous energies involved in these things. This is just an artist's conception, but if you imagine that was a 10-kilometer, I mean, this is a Chicxulub type event, say, 65 million years ago. So say that was a 10-kilometer diameter object. Coming in, impacts in the ocean, in the case of the Chicxulub event, very shallow ocean off the Yucatan, what is now the Yucatan. But the dynamics are that thing is coming in at about 10 times the speed of a high-speed rifle bullet. So it comes through the atmosphere in a matter of a couple of seconds, 4 or 5 seconds, from the very top of the atmosphere until it hits the ocean. The atmosphere hasn't done anything to it. When you're talking about something very small, fine, it burns up. I mean, shooting stars come in the same speed, but they're gone in a fraction of a second. But when you're talking about a mass like that, 10 kilometers in diameter, the atmosphere is insignificant. In fact, the water is insignificant, and to an amazing extent, the land is insignificant. That asteroid, 10-kilometer job, would have penetrated to the bottom of the ocean no matter where it hit. It would have gone down between 30 and 40 kilometers, 3 to 4 of its own diameters, down into the solid Earth below the ocean. And by that time, and that's in a matter of a couple of seconds, and by that time, it's all of that energy, that kinetic energy, has been converted into heat and shock waves, which cause it to explode. And I don't mean fracture, I mean explode. Thousands of nuclear weapons, hundreds of thousands of nuclear weapons in one place at one time. But now it's 30 kilometers down below the surface. And so when it explodes, it takes out a cone of the Earth, which is billions of times greater mass than the mass of the asteroid. And it throws all of that material back up into the atmosphere. Some of it, in fact, a small percentage of it, actually ends up going back up into space on a rebound, later on to land on Mars or Venus or somewhere else maybe. But most of it, of course, ends up being vaporized, broken into rocks, but things of all different sizes get thrown up. Each of those rocks and boulders being thrown up at ICBM type velocities end up going out into space, coming back down on a trajectory halfway around the world or more, and as they're coming back in from space on ICBM type trajectories, they're heating up the same way that the asteroid did, except they're much smaller now. So they're burning up in the atmosphere. So an hour after this has happened, no matter where you are on the surface of the Earth, you're looking up and the sky is lit up with things coming in, some of them reaching the surface, but all of them heating up the sky to the point where the sky itself gets so hot that anything that's flammable bursts into flame. So all around the planet, an hour after this type of an event, you've got not only all the rock and gas vapor that came from this event, this primary event, but now you've added smoke to it from all of the flammable materials. Now, that's pretty impressive. Obviously, the smaller ones don't have that same global effect. But I think the one thing that Norm said that really got me more than that was that because of that extreme temperature of the sky, 1,500 degrees or so Fahrenheit, seawater begins to boil. I mean, all liquid on the surface begins to, if it's green and growing, it burns. If it's water, it's going to start boiling. And something on the order of, from the Chicxulub event, something on the order of about 1 meter of sea level boiled off. Now, if you know anything about the heat of vaporization, you've done any study of physics of boiling something, that is an incredible amount of energy that you're talking about, to boil off 1 meter of sea level. So that really got my attention in terms of the perspective of the energies that you're talking about with impacts of this kind. Now, interestingly, and I don't want to go into it any further, but Norm's statistical analysis indicated that in all likelihood we had things 10 times that size hit the Earth in the 4.5 billion years of Earth's history. Now, when you have something that's 200 meters in diameter hitting the Earth, and the probability, I think, for that one is about 50-50, but something like 200 meters boils off the entire ocean, all the way down to the bottom everywhere. And yet, life survives. And that's the amazing thing. Okay, so let me go on quickly now. The progression of our knowledge of near-Earth objects. Yeah.
Would it condense again eventually?
Yeah. Oh, yeah. Yeah. But it may be, something like a 200-meter thing. You're talking probably hundreds of thousands of years, probably, before you're back to a stable. But remember, the frequency of these things is so tremendous. I mean, it was, 65 million years ago when the Chicxulub event occurred, okay? If the solar system was formed 4.5 billion years ago, make that a year ago, okay? January 1st a year ago, and now we're at December 31st, about to pass through midnight. Where is 65 million years ago? Before or after June? Let's say after June. How many people after June? Okay. You're right. How about after October? How many people think it's after October? Okay, how many people think before December? Well, December 27th. Okay? It just happened, But we don't think of dinosaurs having just been here. But 65 million years ago was 3 days ago, in terms of one day being the length of the formation of the solar system. So, I mean, these things are not, this was not part of what you've probably heard from Lynn and others, the late heavy bombardment. I mean, this is steady state stuff. We're talking a shooting gallery of near-Earth objects, which is a steady state flux of things that are hitting the Earth. And it's been pretty much steady state for the last 3.9 billion years on that order, until at the end of the late heavy bombardment. But in any event, we didn't know much about that. 1830, we had a couple of asteroids, 1900, 1950, etc., 1999. Now it's pretty clear. You're looking at the concentration of the main asteroid belt, And here in the inner part of the solar system, though, you've got things going around in there. And those are the near-Earth objects. The near-Earth objects are asteroids, which, or near-Earth comets, but let's just talk asteroids. Asteroids whose orbits come into the inner solar system basically to cross the orbit of the Earth. They come in to distances less than 1 AU. Now, this is a 2008 snapshot. Again, here each green dot is a main belt asteroid. The red ones are near-Earth objects. And the green ones that we know of now, and all of these are known objects. That is not statistical things, but we've seen each of them in a telescope, we've tracked them, we have their orbits in a database, etc. The same thing with the red ones, and let me tell you, the red ones are only the the potentially hazardous asteroids. If we fill this in with all of them down to even small things like 6 or 7 meters, I mean the size of this room, that we know about, it would be almost solid. And within the next 10 to 15 years, in fact, this whole inner part of the solar system will be solid red. Why do I say that? Because the discovery rate, although it's been high, is going to go screaming through the ceiling within the next 10 to 15 years. Now that's kind of a static shot. That's a snapshot. So all these things are individual points. But in fact, remember, they move around in orbits. And those orbits go around the sun the same way we do. We're neighbors. So you're talking about repetitive passes on all these things. Again, I don't want to belabor it. You guys know that. The result of all of that is the surface of the moon or the surface of Mercury over here. And the Earth would look like that if it were not for our atmosphere and weather and climate and tectonics and blah, 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 blah. We just happen to have a pretty handy eraser in our local environment, but the Earth would look even more saturated with craters if it weren't for that than our moon. So the moon is a great testimonial for the reality of the environment that we live in. And of course there are a few scars on the Earth. If you haven't been to Meteor Crater and you ever get a chance, do it. It's really worth going out there and going to the visitor center over here and looking at that crater. I mean, that's it's impressive when you look at it in a photograph. Let me tell you, when you're standing on the rim of it and looking around, and when you're down in the middle of it, which I did with Gene Shoemaker, in fact. Yeah, it was fun. And of course, up in Canada, you've got the Manicouagan crater and Twin Lakes, and there are another 190 of these things around, scars around the Earth. Well, here we are with the Tree of Life, back to your biology subject, and many different presentations of the Tree of Life, but all of you know that we've got 3 families down here: Archaea, and Bacteria, and Eukarya, and we're always way out on the end of one of these limbs. And obviously, I mean, it doesn't take a rocket scientist to figure out that if you're way out on the end of something, you're probably a lot more vulnerable than things down near the trunk, and that's certainly true. All of your extremophiles that you've been looking at are down here in the lower part of any one of these diagrams. And so they're a lot more robust. The episode that we talked about with Chicxulub, or something even bigger than that, and boiling off seawater, the issue is, and the key word is refugia. I don't know whether you guys have used that word or not, but
I'm not sure I have.
Okay, but you're talking refuge. I mean, because life grows up again. And so what happens when you boil off all the seawater, you say, well, where the hell is the refuge for life there? Well, it's down in a volcanic vent at the bottom of the former ocean. It may be a methanophile or whatever, but, life, once it got a hold, is tough to wipe out. But unlike what most people think about when they think about the Tree of Life, you tend to think, maybe you don't, but let me say, if you don't, you're an exceptional group. Certainly anybody older than you guys, it's planted in your head. There's a kind of monotonic progression of of complexity in life, etc. You know, not so. You know, there's an asteroid impact. Okay, there's another one. There's another one. Every asteroid impact, big ones, have their own signature. They're all going to be different. And some of them hit deep, and some of them, you know, are relatively shallow and only wipe out things on one branch. But the tree of life has been slashed by what I call the crazy cosmic gardener time and again and again and again. And 1,000 years, 10,000, 100,000 years later, it's all growing back out again in a variety which is even greater than the variety that existed before that impact. Some of them are really deep. They cut almost down to the, you know, to the base. But once again, they end up coming back out. But life was not some monotonic thing. I mean, the crazy cosmic gardener came along with a machete and wiped out all different shapes on cutting into the tree of life. And so life has gone up and down, diversity, wiping it out, etc. And we're still in that $4.5 billion process. And what we're saying right now is, fine, let's knock it off. Let's fire the crazy cosmic gardener. And we can do it. And that's the reality that we decided to take on when we formed the 612 Foundation back in 2001. If you look at our marriage with machines and you say, what kind of capability do we have? Do we really have the kind of capability where we can stop this process? And when you think about, seriously, the idea, just the very idea, forget the reality, just the idea of human beings stopping a cosmic process that's gone on for 4.5 billion years and saying, the end, that's an unbelievably egotistical thing to even imagine. But the reality is that we can do that. So that's what we're looking at. This happens to be an image, by the way, of a sort of Itokawa-like asteroid and sort of a typical spacecraft, but that's a gravitational tractor, or a gravity tractor. And that little gravity tractor, which, you know, again, some of you are music majors and other things, but you all recognize that there's a difference between mass and weight, okay? If that gravity tractor is hovering there in front of that asteroid, you know, its mass is the same thing that it was when it left the Earth. But its weight now, the weight is measured by its gravitational attraction of that asteroid. And the weight, I don't have anything around here. Yeah, well, no, I don't. But the weight of that asteroid there is about like that. It's less than that. It's like one page, you know, of a 8.5 by 11 sheet of paper. That's all that thing weighs. And when it's hovering there, staying in front of that asteroid so it doesn't slowly fall into it, it's pulling that asteroid with that amount of force, the weight of one piece of paper or something like that. But it does it for, you know, using ion engines, it's going to do it for whatever time it takes. A couple weeks, a couple months, a year or more. And you don't have to change its speed very much. That's the other thing that's wonderful about orbital mechanics. You don't have to change its speed very much, and you want to change it precisely, and that's what the gravitational attractor will enable us to do. So if you want to protect the Earth, you got three things you got to do. You got to, oops, pardon me, go back. You got to know what's coming at you. You got to have some early warning. You got to have some capability to deflect it, and our argument is it needs to be a proven capability. You don't want to do it for the first time for real. And the third thing that you got to have in order to really take action is you got to have a decision process which is in place and ready to go, and it has to be international, and we'll get into that a little bit in a few minutes. Let me go back at this point. Let me give you a metaphor that helps in thinking about this. Think about standing at home plate and having a bunch of yo-yos out around second base throwing fastballs at your head. Okay? And they got an infinite supply of fastballs. And some of them are big, some of them are small, some of them are cue balls, some of them are ping pong balls, but they're throwing things at your head. And you're standing there at home plate with your eyes closed. You don't know diddly squat, right? One hits you in the head, you're dead. If it doesn't hit you in the head, you're alive. And that's what we've been doing for the last million years, or whatever date you want to give it. But that's what we've been doing up until now. And recently, we've begun just opening one eye a little bit. And we notice things coming whizzing past our head. We're saying, oh, something is flying by us here. I'll bet that once in a while one's going to hit me. But you can't see very well, you're only seeing the big ones. Okay, but as you open your eyes wider and wider, you're realizing that these things are coming at you. Some of them are really dangerous, and you're looking upstream now, and if one looks like it's headed for your head, you're involuntarily going to duck. And you're involuntarily going to duck because you're a single organism, and your muscles and your brain are all tied together. But if you do that, if you think about the whole society, the culture, the planet, life on the planet doing that, that automatic reaction is not exactly there. The brain is there, it's a sort of collective brain, but getting it to take action is not simple. Now the other part about the metaphor which you should think about is that you're going to duck only for the things that look like they're going to hit you. There's no sense in wasting the energy of ducking when something clearly is going to go flying feet away from your head. It's not a real threat. But on the other hand, some of these things are coming at you fast enough that you can't really wait until you know that that metaphor is what you want to keep in mind as we think about near-Earth objects, because it's exactly right. We're going to have to take action with regard to near-Earth objects in the next 10 to 15 years, because there are going to be many objects that we will discover which will appear that they could hit us. And we can't wait until we know for certain, because by that time it's too late to act. So that's part of the early warning process, is to give us quality data early enough that we can act and prevent a disaster. And we do that with telescopes, and I'm sure some of you know a lot about this. I don't know, Lynn, how much you've gone through on this, but the Spaceguard Survey started back in 1998, and the first goal was to find 90% of NEOs 1 kilometer in diameter by the end of last year, by 2008. And we got to about 82%. Didn't meet the 90%, but who cares? That's not the point. There are, we know from statistical analysis, a population of about 940 of those, and in fact we found so far about 768 as of this morning.
This comes up every year. Can you explain how you know there are probably about 940? How do we know that we're 82% there?
Okay, there are a number of independent ways in which you can determine statistically a population, the size of a population. The easiest way to think about it, I mean, this floor is a good example here because it's got nice little squares on it. But if you blew this, take a big farm somewhere, okay, and make it Oregon or somewhere that's damp, and you like mushrooms, all right? So here you go, you're going to go collect mushrooms. Thinking, well, maybe I'll make a business of it or something, so you got to do a business plan. All right, so how many mushrooms are there? What's the population of mushrooms on this farm? All right, well, one way you can figure it out is take a typical square, 1 square meter or whatever it is, and go out there and find all the mushrooms in it and multiply by the number of square meters in the farm. Say, oh, well, I found 100, but there's 100 times as much area, so it's, 10,000 or something like that, okay? That's the population. So by sampling, typically, by doing a sample, you can then project ahead to what the total population is. Another way is you can look at an analog. Look at the moon. The moon has got craters on it since the day one. And you can count craters, you can correlate them with different sizes, okay, the impact energies, etc. So you can make a count and do a statistical distribution of different size craters on the moon and project that to the Earth with additional gravitational focusing and blah, 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 using all your head and all the genius that you got in there, and you can come up with a statistical distribution that way. So there's a whole set of different mechanisms that you can use. And once you start a survey, especially with something like near-Earth objects, not something like mushrooms where they don't move around, but something like near-Earth objects, it's pretty easy to imagine. I mean, just picture you're at the point where you've already discovered 90% of the near-Earth objects. Well, if you've discovered 90% of the near-Earth objects, but you're still searching, okay, and in your general search one evening, or let's say 1 year, you total it all up and you realize that of all the near-Earth objects you found that year, only 10% of them are new ones. 90% of them are rediscoveries. You're discovering one that you've already got in your database. And of course, as you get closer and closer to completion, you're going to be rediscovering almost everything, and you're going to have very few new discoveries. So that ratio also gives you a way in which you can estimate the total population based upon the rediscovery rate. Okay? So there are a number of different ways in which we've been able to estimate the population, and I can show you later the direct size frequency diagram, which shows you. I've got a hokey one in here because it's an easier one to explain to people. Okay, so we've got these telescopes, part of the Spaceguard Survey, and the important thing, and the reason why I've put all this energy into it, and I'm, beating on the United Nations and things of that kind, is because these telescopes are going to be replaced in the next few years, over the next 5 to 10 years, with a couple of much larger telescopes, and our discovery rate is going to go skyward. It's going to go rapidly increasing, and I'll show you what that amounts to. Here is the discovery rate, the blue one. This is dates from, I think, I don't remember what that is, I can't read it from here, but at any rate, this is 1998, this is today. So for that 10 years, here's where the Spaceguard Survey started, and you can see that it bent upward. If I take this out to 2020 or so, then if I take this point, it's out the top, it's about a 40-story building high by this point. We're going to be discovering 100 times as many objects in the next 10 to 15 years as we've already discovered. And that means that, let me see if I've got that. Okay, so here we go. This is a hokey version of Alan Harris's chart, Lynn, but it's got a nice simple straight line compared with his detail. So this is a size frequency diagram. You've got the total number of objects of various sizes here. This is the impact frequency, or the interval in years. And here is the impact energy and the size. So if you just take something 1 kilometer, that was what the Spaceguard Survey goal was, 1 kilometer. You go up to the blue dotted line and over to the left. And in fact, that's a little bit high. There should be about 940 is the total population of objects of that size. We get down to 140 meters, which is the next goal that the Congress set for NASA. Now you're talking about something on the order of 100,000 objects. I guess I'm stepping on a cord. So as you go to smaller and smaller objects, the numbers go up very rapidly. And of course, we all understand that. Lots of things in nature with that kind of a constant power law distribution. The question, though, that's relevant for us as human beings is, well, shooting stars don't do us any harm. Things that are the size of the Chicxulub impact wipe out dinosaurs, and we have mass extinctions. So where is the minimum size that can hurt people on the ground? Okay. In other words, how good is the atmosphere? And basically it turns out that that's around 40 to 45 meters in diameter. Below that, the atmosphere will stop things. Above that size, they do harm on the ground. So that happens to be about the size of the Tunguska impact in 1908, 100 years ago last June. 40 to 45 meter diameter asteroid impacted the Earth, came in over Siberia, blew down, never reached the ground, blew up in the low atmosphere and wiped out 2,000 square kilometers of Siberian forest. If it happened over a city, it would wipe out everybody in the city. And that's the smallest one that we basically are saying we really ought to be paying attention to. And there are something like 1 million of those out there, compared with 1,000 of these. So you're talking about many, many more objects. You're talking about 1 million objects that we've basically got to find and track and predict are going to hit us or miss us, which is normally the case. But once in a while, in fact, if you, again, take that and come over here, what you're going to see is that we get hit by an object like that about once every 500 years. Okay? So that's the frequency with which we get hit. But now go back to what I said about that metaphor. You're going to have to duck more often than you would get hit if you didn't duck. Because you have to duck based on things that look like they're going to hit you. So if you're going to have to duck based on the velocity of it coming at you, your reaction time, you know, you got to launch something, you got to rendezvous with it, you got to build and manufacture the launch vehicle. You got to, after you deflect it, you got to have time for that deflection to take effect, etc. So you're talking 25 years or something like that, 15 to 25 years of lead time. Okay? So we're going to have to duck when the probability of impact looks like maybe 1 in 10, 1 in 50, or something like that. So if the probability, if we're going to have to duck when we're not certain and the probability is only 1 in 50, then what that says is we're going to have to duck 50 times more frequently than we would actually get hit. If we get hit once every 500 years, in reality, then we're going to have to duck about once every 10 years. And that's why we're going to the United Nations, because in the next 10 to 15 years, the international community is going to have to decide, okay, here's one that's looking like it's headed for us, do we or don't we duck? Okay, that's the challenge, the geopolitical challenge that we have. Okay, well, I'm going to very rapidly go through. You know, there's several so what do we do? The second item now, past early warning. What do we do?
You're going to the United Nations. Then who would be responsible for taking action?
Well, we've written a report here, which is on the web. You guys can access it. This is formally being introduced in the United Nations in Vienna next week. In fact, yeah, next Monday, actually. I'm leaving on Thursday this week for Vienna. We've developed this report with an international panel over the last 3 years. We've got a whole set of recommendations, for the international community. We can talk about that a little bit more. Let me just sort of logically go through this. So, can you do something? Pardon me. The answer is yes. Kinetic impact. Many of you remember July 4th of 2005, we ran into Comet Tempel 1. That's a picture of it running into something, kinetic impact. You rear-end it, okay? It doesn't matter what you hit it with. You can take a communication satellite, run it into it. You can run a hunk of lead into it. You can run sand into it. Doesn't matter. If you rear-end it, you're going to change its velocity a little bit. You do that at the right time, at the right amount of velocity, etc., and you can change its velocity by something like 1/10 of a mile an hour out of 67,000 miles an hour, okay, or something like that. And 1/10 of a mile an hour, or even less, is enough that 10 years later, instead of hitting the Earth is going to go through the intersection and then the asteroid. The asteroid will be a little bit late going through the intersection, and it'll go behind it. Or you can hit it the other way, and the asteroid will arrive at the intersection a little ahead of the Earth and goes through the intersection and then the Earth. All you want to do is miss that intersection that would have occurred if you didn't do anything. Okay? So you just want to make it arrive a little early or a little late and it goes by the Earth. Yeah.
So if you're only sort of sure,
If you're only,
if there's only like a 1 in 50 chance,
yeah.
wouldn't pushing it a lot of times actually just cause it to impact the Earth?
Yeah, it would. And in fact, what you do, though, is you don't push it unless you have to. The difference, in a place where the metaphor breaks down, is that one of the first things you do is you go up there with this little gravity tractor spacecraft first. You don't do that first. You go up there with a gravity tractor spacecraft. The problem with our ability to predict an impact is that we have imperfect measurements. Telescopes from the ground see points out in space as little blurry, little fuzzballs. And they're not perfect. No information, no measurement that anybody ever makes is perfect. Everything has a small uncertainty in it. And when you project an uncertainty forward over time, it's going to grow. And so our uncertainty in the knowledge of whether it's going to hit the Earth is due to that measurement uncertainty, compounded by a few other things that we don't know perfectly, like the mass of the Earth, or the obliqueness of the sun, things of that kind. But largely, it's the measurement uncertainty. So what we do is we go up there with a spacecraft and we fly formation with the asteroid that we think is headed for our head. And now we have a radio transponder on that spacecraft, so that we can measure where that spacecraft is with about 10 to 100 times the accuracy of what we have here on the asteroid. So by flying formation with it for a few days, actually it turns out, and tracking the spacecraft from the ground and also getting the relative position between the two from the spacecraft, we can narrow down, we can tell then, is it or is it not going to hit the Earth? Okay? So the first thing you do is you go up there and you get an accurate orbit by flying next to it. But that costs you $300 million. Okay? So somebody's got to pay.
Doesn't that move it too?
Well, yes and no. We're getting ahead of the story. The answer is that this is a wimpy, you're talking about a gravitational tow rope. That's a really, really wimpy force. Okay, this is a much stronger force by running into it. But the effect of this is quite uncertain. Okay, it's just like rear-ending a car in front of you. Yeah, you might bounce him into the guy in front of him, you might not, or you might wipe out 7 cars in front of him in a line. While this is simple and effective, it's also very uncertain. This one, on the other hand, is wimpy. It has very, very little force. I mean, it's not even a parking tap. Okay, but it's very precise. Because of that transponder on board, you know exactly what change you've made in the orbit of the asteroid, precisely. And when you get the right change made, you stop. So you can make a very accurate change here. So in general, and I don't want to go into it in great depth, but in general, what you have to do for most, I don't even want to say it, let me say for a number of different impact scenarios, the first thing you need to do is make it miss the Earth if it's headed directly for the Earth. And then the second thing you have to do is come up with this spacecraft. There we go. Got ahead of myself. And trim it up, okay? Make a small adjustment for precision. If the kinetic impact isn't strong enough, you can fly by it with a nuclear weapon and blow it off as it comes nearby. You don't hit it, you don't destroy it, you don't break it up into a million different impactors. But what you do is you fly very close to it and blow off the nuclear weapon. By the way, that's the Roman Colosseum on Ithaca, just for funsies. But when the nuclear weapon blows off here, the neutron flux heats up that side of the NEO so extreme that it vaporizes and blows off like a rocket exhaust and pushes the asteroid in the opposite direction. But you're talking about nukes in space. Nobody likes the idea of flying nuclear weapons in space or nuclear weapon or any kind of weapons being in space. So internationally, this is a no-no. Nobody likes this idea, especially the idea of the U.S. military, oh yeah, don't worry about it, we'll take care of it, right? Right. Okay. So we're gonna do
One
just
question.
yeah. Yeah.
Yeah, so I noticed when we were talking about all these techniques that we were talking about kind of isolated asteroids that are, I guess, out to Earth. But to what extent if there's so many objects flying around, like how much are they interconnected? And I guess when you're looking into this, are there a lot of computer simulations that need to be done that would address like maybe possible chain reactions? Like if you throw one asteroid onto a different course, how will that affect other asteroids?
Well, if you just think about it for a minute. If you think about an asteroid, even the most frequent ones that we're concerned with, the 45-meter jobs, hitting the Earth once every 500 years. Think about the cross-sectional area of the Earth and another asteroid. I mean, asteroids are minuscule compared with the size of the Earth, and all you're going to do is multiply by that ratio, you know. So you're going to divide the frequency with which an asteroid is going to get hit, say once every 500 years, by 1,000,000 or something like that, or more. And it's going to take an asteroid will hit an asteroid, and if you look at pictures of asteroids, you're going to see they have craters on them, so they do hit each other. But you're talking over millions, hundreds of millions, billions of years. So, you know, while asteroids do, especially ones that go looping out through the main belt, every once in a while, every few thousand years, they'll come close enough to another one that it'll slightly affect its orbit. It's extremely rare that happens. I mean, space is big. You have to really get that through your head. So you don't have a chain reaction. I mean, you know, these things are, you know, there are millions of them, but you're talking a lot of space out there. So when you plot the orbit of one of these things, provided you have measured it right and you take account, I mean, every night when a new asteroid is found, and generally speaking, you're talking once a night or something like that, once every other day, its orbit is determined and it's projected forward 100 years by the best simulations that we've got, okay? And it's, so and if we have, you know, internet here, I could bring up this stuff. It's all on the web. It's publicly available. And if you look at it, you can see the probability of impact of the 200 and some objects which have some probability of hitting the Earth in the next 100 years. Out of 6,000 we found so far, 5,775 of them, or something like that, has 0 chance of hitting the Earth in the next 100 years. But the remaining 238, as of this morning, do have a chance of hitting the Earth in the next 100 years. Low probability for each of them, but a non-zero probability, okay? So that's the process. It's done every night. And JPL and Minor Planet Center, that's the database that we're building up. This is, I want to go into the geopolitical things now. If you picture that you're the asteroid Apophis, which is going to come very near the Earth in 2029 and may come back for an impact in 2036. Okay, this is one of the 238 I just mentioned that has a non-zero probability of impact. Okay? And on Friday the 13th, as a matter of fact, of April 2029, it will come about 5.5 Earth radii. It'll come by, if this is the Earth, and the Earth is moving from left to right. In other words, you're sort of looking at the sun, looking toward the sun here. The Earth is moving from left to right. That asteroid is going to go by about over here, okay? However, it could, in fact, go by anywhere, well, let me put it this way. If it goes by a certain point out here in 7 years later, in 2036, it will come by again. And now the uncertainty goes from over there to way out that side. But that line of uncertainty crosses the Earth right here. So that line is, let me say, the overall length of that line of uncertainty is, say, 45,000 times that distance. Okay, so 20,000 times that line goes out there, and way out here. But it does cross the Earth. The portion that crosses the Earth is about 1/45,000th of the total length of the line. That's not quite right. I mean, that's a flat distribution. These things don't have a flat distribution of probability, but roughly speaking, that's what you're talking about. So what you can say is, today, we can calculate the length of that uncertainty line, and we can know what the width of the Earth is, and you're saying the probability of that impact occurring in 2036 is 1 in 45,000. Another way of saying it, and the reason that I've drawn this map and plotted that line across there, is to say that if Apophis hits the Earth in 2036, it will hit somewhere on that line. Not down here or up there, or whatever. It's going to hit somewhere within that narrow corridor. We call that the risk corridor. This is the risk corridor for Apophis, but each asteroid, which has a probability of hitting the Earth, has a line similar to that. It's a straight line. That's the intersection of the plane of the NEO orbit with the Earth at the time of the intersection. Okay? Now, if you tilt the Earth down, that's what that line looks like when you tilt the Earth down, or like this if you tilt it 90 degrees, or if you blow up this section right in here, there it is, that line coming across the border between Costa Rica and Nicaragua, and across the northern edge of Colombia and Venezuela. Now, I don't have it shown in here, but you can see a picture of me talking with the president of Costa Rica about this. And I've also met with the secretary, the president of the General Assembly of the United Nations, who happens to be Father Miguel Descoto Brockman, who is a Nicaraguan. Okay? So people who live along here take a real interest in this probability that they may get hit by the asteroid Apophis in 2036, on Easter Sunday, by the way. Again, April 13th. That's what that line looks like. Okay, this is the Apophis risk corridor. Okay, so in 2036, a probability of 1 in 45,000 that Apophis will hit somewhere along that line. And as we measure Apophis more and more with our ground telescopes, that probability will in all likelihood go to 0 at some point. But one case out of 45,000, it's going to not go to 0, it's going to go up to 1. Okay? Yeah?
How large is Apophis?
Apophis is about 1,000 feet in diameter, 280 meters in diameter. If it hits, it would have an energy impact of about 650, 700 megatons of energy. It would, if it hit out here, say in the Pacific, let's say midway along its risk corridor, the tsunami that it caused would wipe out the coastline of North America, the western coastline of North America. People have done made economic damage models. The estimate of an Apophis impact here in terms of economics is about a $400 billion destructive event. Okay? Now it's going to cost to deflect Apophis something on the order of $500 million. 500 million compared with 500 billion. Okay, you spend $1 for insurance against $1,000. That's the kind of choice that somebody's got to make. Now, who makes that choice? I mean, it doesn't directly threaten the United States. It does in terms of a tsunami. But if you're going to slow down, pick what we said before. The trick with deflecting an asteroid is to slow it down a little bit so it arrives late, or to speed it up so it arrives early, before the Earth gets there. Okay? Now, you can picture that if you do that gradually, you start slowing it down, then what's going to happen is it's going to end up coming later and later. Well, if the Earth is moving from left to right, that means instead of hitting here, it's going to hit over here. You slow it down a little more, it's going to hit here. If you stop slowing it down. What you want to do is you want to slow it down until you take it over here, off the Earth. Or you want to cause it to arrive early so that it ends up going through the intersection here in front of the Earth. Okay? But the process of doing that, if something happens in the middle of that deflection to take it off the backside of the Earth, it's going to end up hitting over here. So these people over here in Japan and Korea and Russia end up having an increased risk if you take it off the backside of the Earth. But that's what the Costa Ricans want to do, because if you take it off the leading edge of the Earth, the way the Japanese want to do, then you have a chance of hitting Costa Rica and Nicaragua. So the point here, from a geopolitical point of view, is anytime you're going to deflect an asteroid to reduce the impact to everybody to 0, you temporarily increase the risk to somebody who was not initially at risk. Who does that? Who makes that decision? On what do you base such a decision? That is a political decision. It's not a technical issue. Okay? This is a political decision. Somebody's got to decide to do it. This is intrinsically, deflecting an asteroid is intrinsically an international issue. The United States isn't going to save everybody else's butt here. The U.S. taxpayers don't like it when their money gets spent to deal with somebody else on a risk that they may not even believe in. If you think they don't believe in bailing out the banks on Wall Street, think about this one. Okay? Now, as I said, this is a real risk corridor for a real asteroid we are currently tracking. Okay? But we're going to find 1 million asteroids in the next 10 to 15 years, and if I take things of comparable risk, that's what it's going to look like in 2020. These are hypothetical, to be sure, but that's the kind of randomized distribution of risk corridors that you're going to have by 2020. Every country needs to be dealing with this issue because everybody's going to have one of these things going across it. So that's what we've been involved in. This is back of my head making a presentation to the United Nations in Vienna 2 years ago. I'm about to be there in the same place next Monday, presenting our recommended decision process for the nations of the world. To say, get ready, you're going to have to make decisions in a timely way. You can't, when you've decided something's coming at your head and you better duck collectively, okay, you can't start debating it then for the next 20 years, the way the United Nations generally does with things. We've got to go through these scenarios ahead of time and set up criteria so that when it comes time to make a decision, we can make it and we can duck in a timely way. So that's the challenge for the United Nations, and that's where I'll be headed next week. This is the group of international experts that help the Association of Space Explorers put this together, and we've got former ambassadors and various diplomats and space law specialists and legal specialists and advisors to presidents and the president of the Royal Society of the UK and on and on and on. Insurance specialists, we've got all kinds of experts here, very few of them being technical experts. This is not a technical issue. This is a political issue, and it's an international political issue, and that's what we've addressed with this. So that's the status of saving the world. Oh, there I am. Oh, I did have it in here. This is President Oscar Arias from Costa Rica. In fact, this is Earth University, which is in Costa Rica. We had our third of our 4 workshops that we put this report together in Costa Rica, and this was a meeting that I had with the president afterward. And this is the Nicaraguan president of the UN General Assembly, and he's a Jesuit priest, as a matter of fact, Father Miguel Descoto. delightful guy, an old Sandinista. He really is a wonderful, wonderful man. And these are two of the members of my panel on the outside. So there's the report.
You said we can get that online?
Yeah. And this goes back to the other word slide. We're not unique in the universe. You've all gotten briefings from Jeff Marcy and from other people, you know. If there's life out there, okay, all solar systems have, most solar systems probably have asteroids, comets. This is a common problem. If we don't solve this problem, we go the way of the dinosaurs. If we're not ready to make these decisions, then in fact, we don't join the crowd out there, assuming there is a crowd. Okay? So this is our final exam in a way. You know, are we ready to take the exam? That's the question I'm asking the delegates of the United Nations next week. Thank you.
I know it's getting a little late, but that was absolutely stunning, both parts. Are there any more questions right now that, what?
I just wanted to ask, fairly on a kind of humanistic level, we're concerned about asteroids again, but is there no concern about kind of throwing off a historical evolutionary process in, like, you know, for millions of years in the future, that it just something that shifted, that, you know, that had, we didn't interfere with before, and this is where we are now, if we didn't interfere.
I'm sorry, I'm missing the question. Can you repeat it for me?
I didn't quite hear.
Yeah, go ahead. Do it again, I'm sorry. My hearing isn't as good as
Okay, so I'm just wondering if there's any concern about on a evolutionary level, right? If we do kind of stop the hitting of asteroids on Earth,
Right.
which has told evolution over what millions of years, there's no concern about what the changes would be like.
Well, sure. Do you want to take that chance? You want to commit suicide for what might happen? Go ahead. I can't buy that argument. I mean, that's the argument that says, you know, if I don't take this, if I don't use my brains to do the kinds of things that I can do, then somebody else might do it, and they might do it even better. So I shouldn't even try. Here we are, at the, in a sense, at the top of the evolutionary ladder, at least in terms of, you know, being able to make machines and control the environment and that kind of thing. I don't know where this evolutionary experiment is leading. There's no question if we don't use our brains and our machines the way I'm proposing here, that we are going to go the way of the dinosaurs, sooner or later. It's only a matter of when, okay? So sooner or later that's going to happen. In fact, we might just blow ourselves all up anyway, you know, even if we do this, and that's fine. That would be the end of the experiment. But at least if we want to have the experiment we're involved in our corner of the universe continue to see where it goes, then we do this. And we protect ourselves from this extinction level threat. Now, is that going to be a good thing or a bad thing? That's a really weird academic question, but you know, we can certainly come down on that side of it. My own preference is to say, you know, I've got a brain, as we've evolved to this point, I can stop this. That's an evolutionary development. So to me, it's evolutionary, it's a positive evolutionary thing.
When you drew that map, when you showed us the map of NEO objects with like all the green dots and as many as they got, if you had drawn that map to scale, including the asteroids to scale, would we have even noticed them?
No. No. I mean, you know, they're two different things. Number one, the size of the dots is, you wouldn't even show up, obviously. But in addition to that, even if they did show up, some of them are down, or, you know, there's a three-dimensional aspect to it. So when you look at the orbit of the Earth and an asteroid crossing, it's not just that it crosses, but they've got to cross at the same depth as well. Okay? But when you've got thousands of them, they come that, you find, well, I mean, there it is. Today, we have 6,000 of them that cross, okay? Of those 6,000, within the next 100 years, 238 of them cross at the right depth, and they have an intersection. Probability of one. Now, again, the asteroid is uncertain. We know where the Earth is going to be in 100 years. But the asteroid may be, that up here on its orbit, or it may be down here. Okay? And we don't know. We have to make more and more measurements, and the uncertainty gets smaller and smaller, so we know more and more accurately. But we never have perfect information, so you have to act based on the best information that you have.
You mentioned the ion drive. Is that what is it? And are there examples of it working at the moment, or is it?
Oh yeah. No, ion engines have been used routinely in space for more than 20 years. They're very weak, but the advantage of an ion, the best descriptor is an electric engine. Okay. Because they're all different kinds. There are Hall thrusters, and there are magneto plasma drives. There are all kinds of different things. Okay, but they're all electric propulsion, which is characterized by using very little fuel. But unlike chemical ignition, you're sending things out the end of the rocket at tens to hundreds of times higher velocity. So you use very little fuel, but it takes a hell of a lot of electricity. Okay? So you're substituting electrical energy for the mass of fuel. But that makes it very cheap to get off the ground because the mass is generally lower. But you accelerate at very, very low speeds. I mean, the Dawn mission, if you want to Google Dawn mission today, has got an ion engine on it, which has been running now for, about 2 years continuously or something like that. I mean, they can run for very, very long periods of time. But they're very wimpy.
No way, I don't know if you caught that point about the asteroid hitting 65 million years ago. The answer to the question of how long it took the dinosaurs to go extinct was what? Less than an hour.
Yeah,
probably
some hangers on for a week or so,
Maybe. the thermophiles.
Yeah, right. The ones on the Atkins diet.
Right. I wanted to thank Rusty one more time because that was just